Hi everyone. In this video I'm gonna show you how you can actually constrain the value of the gravitational constant g via a Universe Sandbox 2 simulation. You can see the setup over here, but you can see there is a mass of 1 kilogram. So the mass is given over here. There's the mass, and this is also mass of 1 kilogram. So they are also spherical symmetric, and they are not moving at the beginning of the simulation, and they are just placed in 50 centimeters away from each other, from the simulation's origin over here and over here as well. So they are just separated by 1 meter. And from that on, we are actually using some physical formula to get the gravitational constant g that I'm showing right now. So basically here we have a gravitational law from Newton. It's just the gravitational forces equal to the gravitational constant g over here times the two masses over distance squared, which means like distance from the center of the bodies, which is given like with these 50 centimeters by times 2, so 1 meter, and they have masses of 1 kilogram. So just in SI units I always get ones later on, but I have already done this setup with different masses and different distances when just showing you again that it is replicable. First of all, we are solving this equation for the gravitational constant over here, which is, so we are measuring the force, the distance, and the masses. And for both masses we have an equilibrium mass. The forces are just the same, but they are just pointing towards opposite directions. They both attract each other. But for Universe Sandbox 2 I did not find a way how to measure forces directly. That's where you can see the setup again with my other masses with 7.2 kilograms and separation of 2 meters. So it's given over here. But for the force over here we use this is the change of momentum. So when the momentum change over time, so this p dot means it's just like the momentum, like mass times velocity, which is changing over time, and this is called a force. And I cannot measure the temporary change directly, therefore I can measure the difference in momentum and difference in time when I want to get this delta t as small as possible. And over there we can insert this for the force, and we are getting this formula at the end. So I measure the difference in velocity. The radius should be relatively constant by very small time interval. It should not change that much, not at least not significantly. And then I also have to measure the time difference and the mass. And for my first setup I got this delta t of 0.284 seconds, and this was the velocity afterwards. So in the beginning they were completely at rest, and the distance was 2 meters at the beginning, so over here, and the delta time was 0.284 seconds. Inserting all of these values in, we got a value of 6.63146 times 10 to the negative 11, which is not that bad, which was not deviating that much, as you can see from the literature here. I have stated a link over here, and we have it here. This is the deviation between the simulation and literature, which was only 0.64%, and I'm just showing this experiment to you again. So here you have, as you have already seen here, the masses of 1 kilogram separated by 1 meter. Then I'll just give the step by just one step. There's the time. The time difference is just 0.00176 seconds. and we also have kind of velocity, which is 1.17 times 10 to the negative 12 meters per second, and these are my values that I have to use. And now I'm going to use a calculator for obtaining values. So basically we have a delta V of 1.17 times 10 to the negative 12, 1.17 times 10 to the negative 12 meters per second, and then we also have to use the distance squared was just 1 meter squared, so it's just a 1. And then next value what I have to insert here is the delta t. This delta t was 0.0176 seconds, 0.0176, and then also have to multiply by the mass, which is just 1 kilogram, and which is the value I got here is 6.647 times 10 to the negative 11. In unit is just cubic meters per kilogram per second squared. So this is a relatively similar value, and from that I can also use this for the deviation calculations. I will do it. 727, I think this is just sufficient. 10 to the negative 11. Then I still use the literature value, which was given here by 6.67430. So this value times 10 to the negative 11. This divided by the simulation value, which was this here, and then I can get a deviation. Deviation is 0.0039, and in percent is just percent. So how many percent is roughly 0.4%. So I basically confirmed my results for the gravitational constant here. And from this, I just wanted to thank you for watching this video, and take care and